a new example today. There's definitely the counter example where our object is perhaps in this arrangement. So our point mass is sitting off here to the side, and this is, I don't know, length D, but they could maybe change where this strikes the object. Does that make sense? Similar sets of cases, right? Also, be aware that this does not have to be the case for this problem. That adds the element of conservation of energy by having this hung vertically. It could be that this whole system is on some kind of horizontal frictionless surface. And when the puck strikes this object, whether it sticks to it or bounces off, the system rotates about its, fixed axis point and is on a horizontal table, so it's not pulled back down due to gravity. Does that make sense? Now, we're also going to see examples where gravity is downwards. The object does bounce off or something like that, so gravity is like this, but then the system oscillates back and forth, which is our next unit. So this being treated as what's called a physical oscillator is also a pretty common kind of question. So we're going to be looking at this a couple more times throughout the year, but for today I want to focus on the collision portions, and I want to look at a different example, but Owen has his hand up.
No, this is not. Sorry.
I want to talk about the situation in which there is no fixed axis point, where the pivot isn't fixed in space. So the example we're going to use is us looking down on, say, a horizontal surface that is frictionless. So this is our frictionless horizontal surface. And we have some sort of collision that's going to take place. In the AP literature and in the textbook literature, this does not occur very often, but it has occurred. And so I want to make sure that we have kind of covered the basics about how this problem is the same as things we've seen before, and how it's also, slightly different, slight modification. So the first thing I want to point out is if there's no fixed pivot point, meaning there's nothing where the rod is attached to the surface, then the conditions for conservation of linear momentum are met because there's no external force acting on the system. So the net change in linear momentum has to be zero. And because our object has extension and the collision is going to occur off-center. Now, I'm using my words carefully here, and I wasn't as careful about the way I spoke in sixth period. So I want to really be very clear. If I was to move this so that I was to strike the center of the rod, and this wouldn't be a particularly interesting question because we could probably stop right with this and realize that this is just a linear momentum question. But the moment I talk about the extension of the object and I make the extension of the object or the shape of the object important, meaning I strike the object off center, well then I do have to take the extension of the rod into account. And now I have to deal with the fact that angular momentum will also be conserved. So this brings two changes to yesterday's discussion. Change number one, we now have a linear momentum problem. That's the first thing, a linear momentum or a collision problem. So all the way back to what we talked about, at the beginning of the semester and the end of last semester, Momentum of object number 1 plus momentum of object number 2 is going to have to equal the momentum of object number 1 plus the momentum of object number 2. This is before and after the collision. So that still exists. However, since our object has extension, it's not a point mass, it has some shape, this now all refers to the center of mass of each object. So when we talk velocity now, we're talking about the velocity of the center of mass of the rod. Point 2, this is a change. They did not give us an axis of rotation. Well, we don't just get to choose one. Objects that have no fixed axis of rotation, that are set into motion, will naturally revolve about their center of mass. So without a fixed axis of rotation, the natural axis of rotation is through the center of mass. Those are two things we have to add to yesterday's discussion. So without a fixed axis of rotation, the center of mass becomes the axis of rotation. That changes quite a bit when it comes to our problem here. So let's consider setting up a simple example of what to do. For this example, let's say I have a small puck with mass m and velocity v that is directed towards just a simple long rod of mass, 3m and length d. I stupidly made it length L in sixth period again. It's going to get you. Let's say during the course of the collision, the following happens. Just 1 second. Let's say that the puck recoils at 1/4 of the velocity off of the rod. But the rod, of course, now begins to move, which is going to include a rotation. Now, in this collision, two things take place. First, if the puck recoils back in the same direction, and I'm trying to be very careful here, if the puck recoils back in the same direction, then the rod is going to have just a linear velocity in the same direction that the puck had originally. Meaning this is still a one-dimensional problem. Now, if the puck bounced off at an angle, then that's not true. But under the circumstances, if the puck struck the rod at a perpendicular, then it should bounce off back along that line. So you have to be careful about the way the problem is phrased, but I don't think they would add a two-dimensional component to the collision. This is already a lot of work as it is. But the rod now has two velocities. It's got a linear velocity, which I'll put v final to indicate that it's the velocity of the rod after the collision. But it's also going to have an angular velocity, omega. And these two are detached, meaning they come from two different things. Now, this problem is going to require us to do two things. First, there's going to be a linear momentum problem. Now, that problem's pretty straightforward. As long as we're careful and understand that it's going to be the momentum of the puck plus 0 because the rod had no linear momentum. And then after the collision, momentum of the puck plus the linear momentum of the center of mass of the rod after the collision. This is a straightforward collision question. Going back to the collisions that we had before, remember for a collision question like this, they've got to give you quite a bit of information. Although we have 3 different kinds of linear collisions, perfectly inelastic, the objects stick together, elastic, like this one, inelastic, like this one. It's not perfectly inelastic because they don't stick together, but kinetic energy is not conserved in this collision. And then there's the possibility of an elastic collision, but I don't see that being a highly likely problem, but we could get any one of those. This one being an inelastic collision, though, they've got to give you something about what happens after the collision, or it can't be solved because it'd be 2 unknowns, both velocities. This one's pretty straightforward, though, because I'm going to have mv for the puck plus 0 for the rod before the collision. And that's got to equal, well, m times negative 1/4 v. The puck rebounds backwards. So these are vectors. I have to choose a direction that I'm going to call positive. So I'm going to call to the right positive. Plus, and be careful here, the rod has a mass of 3m times its velocity vf, or v final. Now, yes, there's math here. You guys can do the math. I don't want to make the math any more than is necessary. Finding the velocity generally is going to be just an exercise. And this will tell you how fast the center of mass of the rod is going. Now, you have to recognize that this is the only way to get the velocity of the center of mass. Can't do it through energy because energy is probably not conserved. There's no way you can deal with forces and stuff here because there's not nearly enough information to deal with forces. This is a collision. You have to recognize for what it is, a collision. Any questions about this? This is pretty simple, right? If I had just had blocks here and it wasn't a rod, that should have been a no-brainer and a very straightforward question. But now we have the second part of this problem. What is the angular velocity of the rod after the collision? That's going to take some work. So part 2 of this problem. Now we have a angular momentum problem. I don't think it's a big reach to say that the only thing with angular momentum before the collision is the puck. But it's important to know that the puck can only have angular momentum relative to a fixed point in space. We have to choose that point. Now, it might not be obvious because there's no fixed pivot point. But remember, when it comes to angular momentum, you choose the appropriate pivot point that brings the system together. Meaning, what is the pivot point for the system? And that's going to be the center of the rod. The rod's going to rotate about its own center. And although the center of the rod will be moving after the collision, remember, a collision is just the instantaneous moment before contact and the instantaneous moment after contact. So the rod will not have had a chance to move by the time you do this calculation. It starts moving after that. And the axis of rotation starts moving after that. But for this problem, the axis of rotation doesn't begin to move until after the puck recoils. So when I start calculating the angular momentum of the puck, I'm going to use this distance to do so. I'm going to use the closest approach distance because we know it's going to strike that rod perpendicular to the rod at the bottom end of the rod. After the collision, the puck still has its own angular momentum. And although this picture shows it advanced for a few moments after the collision, we know that the collision actually is just the instantaneous moment after the two things separate. So the rod will now also have some angular momentum. Remember, angular momentum, R cross P. But I think we've got this mostly handled as R perpendicular MV. By the way, I'm going to be making out of the board positive because the puck has an out of the board angular momentum. If we consider this to be our axis of rotation, then consider the direction of rotation by drawing a line from there to the straight line the puck travels. So right here, going this way, that's a rotation like this. That's out of the board. That makes sense? So, I'll start with d over 2 for my r perpendicular times mv, the linear momentum of the puck. That has to be equal to, well, it's recoiling off of the same point, so that's still d over 2. M times negative 1/4 v. Now, the rod, plus I omega for the rod. Any question about what's here? Now, when you work this out, if omega comes out to be positive, then the rod rotates in the out of the board direction. If the angular momentum comes out to be negative, then you know the rod rotates in the into the board direction. I don't think that's going to be particularly hard to understand, but by putting this explicit negative sign here, we're kind of indicating that we know that the puck is going to have a negative rotation relative to the axis of rotation. And again, I don't think that's a particularly big surprise. Looking at where the puck is relative to this, and the puck's going this way, it's going this way, so that's going to be rotation like this, right? And that's negative because that's, into the board. All right, so again, that's setting it up. Setting it up is the hard part in my estimation. You're solving for omega. That's the easy part. You can combine the numbers together. I will take a few moments just because I want to make sure we point out a few things about this, because there's lots of places to make mistakes. This is going to be dmv over 8. For I, moment of inertia of a rod about its middle. Don't forget to put the mass of the rod here and not just m. Remember, it's d squared all times omega. The important thing about this that I want to make sure I throw in front of you is that your answer for omega is likely to have the size of the rod in it. And that should make sense, because if the rod was a different size, I would expect it to spin differently, because our puck's angular momentum would be different relative to where the center of the rod is. If you don't understand what I'm saying, let's work the answer real quick. I'm going to subtract the 1/2, I'm going to add the 1/2 and the 1/8 together. So I got to get common denominators. That's going to be 4/8, so 5/8. Is that right? Hoping so. 1/8 plus 4/8. And on this side, I'm going to have 1/4 d squared m omega. So I think I'll multiply both sides by 4. That'll make this 5/4. I'll get rid of one of the d's, and I'll get rid of the m's. And I'll get v on this side divided by d equals omega. I'm pretty sure that's going to be our answer then. The things that are here, the number part, there's no way to have predicted that would have been 5/4. I don't think so. But v over d, yeah, if I'm traveling faster, that makes the thing spin faster. I find it interesting that if the bar is longer, do you notice that makes it spin slower? That might be a surprise because you'd think that if the bar was longer, you're getting more torque because you're hitting it further away from the center. But it also means that the puck had more angular momentum relative to the center. And that's why we get this weird kind of inference there. But also, remember, moment of inertia, how much inertia the system has, is strongly dependent on how much that mass is spread out. So this bar is much harder to turn because it's big than it would be if it were small. And the harder to turnness of the rod outweighs the more torque and the more angular momentum the puck has before the collision. And if you didn't catch all of that, I'm not sure that's particularly important. This is a standard problem in which there is no fixed axis of rotation. There is, however, the problem that was on an AP exam within the last 5 years that I should point out because it's like that problem, but enough different to cause some people some sadness. There was a problem a couple of years ago where they had this I only say it was a disc of ice that was on a friction-free pool of water with a person standing on it at one edge. So we're looking down on this. Everybody understand? The first part of the problem, the person on the ice threw a ball this way off of the disc of ice. This is just a momentum question. There's no rotation here. Throwing the ball right there in that direction would cause no rotation to the disc of ice because it's not thrown with any rotational or angular momentum, right? If we look at where it is, the value for R perpendicular would be 0, so it has no angular momentum. That was part A of the problem. Believe it or not, part A of the problem was a projectile problem because they said that the person was so high and they asked questions about where did it land relative to the disc of ice. But they did say that you had to figure out the fact that the disc of ice was pushed to the left because the ball was going to the right. Fair enough? Follow that question so far? Then, part C of the question, I think, the kid turned and threw a different ball this way. Do you see how this problem is going to cause a rotation to the disc of ice? It's also going to cause the center of mass of the disc of ice to go this direction. So we have a conservation of linear momentum problem. This is a version of a perfectly inelastic collision. It's the reverse. We did these problems. This is the lab you did, right? The two cars in the middle, and you separate them with the spring. Did we do that in here? Oh, we should. We will. But we also have this guy throwing the ball, which is going to have an angular momentum, so the whole disc and the person are going to start to rotate this way. All right. A couple of questions. We're talking a very long time ago. There was a question that was related to a combined moment of inertia object that looked like this. It was a bicycle wheel of some sort that had a fixed axis of rotation here. I went back through the entire literature to find the only example of a point mass angular momentum problem where you couldn't use the distance of closest approach. In the problem, they had a dart that was fired right at the edge of the wheel, but it wasn't at the tangent to the wheel here. It was at the edge on one of the spokes. The dart stuck in the wheel and the wheel spun. Is it clear to you that the dart would have angular momentum relative to the wheel? Unfortunately, of course, it strikes here. It doesn't strike here. So it strikes at a distance r away. But they gave the angles. Because they gave the angles, this problem just resorts to RMV sine the angle they gave, because that will be the angle between the torque arm, R, and the momentum, MV. You have to be careful and make sure you get the angle right. Depending on where they give the angle, it might be this angle or its complement, depending on how you're measuring things. Remember, the MV would be this way, so you'd have to use that angle there, which would be the complementary angle. You guys follow a little bit? That's the way this problem is done. Or you could calculate what this distance is from the angle and do it that way. It's the same angle, same value. But I can only find this one example in all the years. And I will make sure you have a copy of it and how to do the solution portion of it. I'm not going to give it to you on a test or anything like that. And it was from like 1976 or 77. So, like I said, I think I was 4 or 5. So we're talking like a long